In this question of magnetic field, we will be only looking at Faraday's law. Let's take a look at this question. A plain loop of wire is placed in a uniform magnetic field. List the ways in which the loop can be moved without producing an induced EMF. Explain why no EMF is induced. In this question, EMF refers to the electromotive force. To answer this question, we need to use Faraday's law of electromagnetic induction. However, this law involves some terms that we may not be familiar with. Let's take a look at some of the terms that are used in this law. One term that you will see is magnetic flux. Magnetic flux is given this symbol phi, and the three loops that you see in the three figures actually represent the plain loop of wire in the question. So, magnetic flux through a plane surface is defined as the product of the flux density B, which is also known as the magnetic field, normal to the surface, and the area A of the surface. The figure on your left shows the magnetic field that is parallel to the normal of area A. The middle figure shows a magnetic field inclined at an angle theta to the normal of the surface. The last figure on your right gives the formula to calculate magnetic flux. When your magnetic field B is at an angle theta to the normal of the area A, the formula is given by phi equal to B cosine theta times A, where theta is the angle between the normal to the plane of the area A and the magnetic field B. Now that we have learned about magnetic flux, let's take a look at Faraday's law of electromagnetic induction. What does that law say? Well, it states that the EMF induced is equal to the rate of change of magnetic flux linkage, N phi. Now, notice previously, we only talked about magnetic flux. We did not mention anything about magnetic flux linkage. The relationship between magnetic flux linkage and magnetic flux is just that factor N that you see in the definition. So magnetic flux just talks about a single term of wire moving through a magnetic field, and the magnetic field lines that goes through the area, we call that magnetic flux. But if that loop of wire has many turns, not just one, perhaps 100 turns, then when magnetic field lines passes through these 100 turns of wire, we call this magnetic flux linkage. So N actually represents the number of turns of the wire. So when magnetic flux linkage changes with time within the wire, EMF is induced in the wire. Let's take a look at the law mathematically. Here we say that induced EMF is proportional to the rate of change of flux linkage. Induced EMF is given this symbol epsilon. And we say that the induced EMF is in the direction that opposes the change of the flux linkage. But we will not go too deep into this part of the proportionality relationship. So induced EMF is equal to the negative of the differentiation of magnetic flux linkage, N phi, with respect to time. We have already mentioned that N is the number of turns of the wire. Now in this question, N is equal to 1 because there's only a plane of loop as stated in the question. So finally, induced EMF is equal to the negative and of the differentiation of N BA cosine theta with respect to time. Since we already knew that phi is BA cosine theta, we can replace phi with BA cosine theta. You will notice there are quite a number of negative signs in the equation. The negative sign actually explains the opposing direction as stated in the proportionality relationship. Now that we have defined Faraday's law, let's proceed to explain why no EMF is induced. No EMF is induced if there is no change in the magnetic flux linking that plane loop of wire. Remember, in this question, n is equal to 1. So we will not be dealing with magnetic flux linkage. Rather, we will be dealing with magnetic flux. So mathematically, induced EMF epsilon is equal to the negative of the differentiation of magnetic flux with respect to time. And we know that magnetic flux is equal to BA cosine theta. So we replace phi with BA cosine theta. So the EMF will be equal to 0 when d phi over dt is equal to 0. So if we move the loop about in the field such that the angle between the magnetic field and the normal to the plane of the loop remains unchanged, then we can say that the magnetic field B and the angle theta are constant, and we can take B cosine theta out of the differentiation operator. How do we know B is constant? Because it is mentioned in the question, the plane loop of wire is placed in a uniform magnetic field. So we know that B must be a constant. And we have made the assumption that we're going to move the loop such that the angle theta does not change with time. Therefore, the product B cosine theta can be taken out of the differentiation operator. So, for the induced EMF to be equal to 0, then the differentiation of the area of the loop with respect to time must be equal to 0. And that will only occur if the area of the loop remains constant. Therefore, one way to move the loop in the uniform magnetic field such that it does not produce an induced EMF is to move the loop in the field such that the angle and the area does not change with time. Let us look at another way to move the loop such that no induced EMF is produced. Now recall, induced EMF is equal to the negative of the magnetic field multiply the differentiation of A cosine theta. Magnetic field B is taken out of the differential operator because B is uniform. It is mentioned in the question that the plane loop of wire is placed in a uniform magnetic field. Therefore, the constant B can be taken out of the differential operator. Now, we want the induced EMF epsilon to be 0. Then, the differentiation of A cosine theta with respect to time must be equal to 0. And that will imply the product A cosine theta is a constant. But we cannot let the angle theta to be constant and the area A to be constant again, because that is already the first way how we will move the loop. Therefore, this time, the second method, we will have to vary the angle theta and the value of A. So, if let's say the angle theta increase, this will imply cosine theta will decrease. And if the angle theta decrease, this will mean cosine theta will increase. Now, when cosine theta decrease, this will mean that our area A will have to increase. Conversely, if the cosine theta increases, then the area have to decrease. Why is this so? Because we want A cosine theta to be constant. And for that to occur, when one variable increases, the other variable must decrease. Hence, the loop can also be rotated such that changes, provided the shape and hence the area of the loop is adjusted at the same time, such that its area A decreases as cosine theta increases, or in other words, when theta decreases, and vice versa as indicated previously. I hope this question will give you a better understanding of Faraday's law. Thank you.